All right, let's jump right in. We're going to explore this really cool connection between a simple, everyday problem and one of the most powerful ideas in all of mathematics. You're going to see how untangling a mess of wires on a circuit board leads us straight to a concept that powers everything from data science to quantum mechanics. So, where do we begin? Not with some dusty old math textbook, that's for sure. We're starting with a real, hands-on puzzle, something you might actually bump into in an electronics class. It's always best to ground ourselves in a real-world problem before we get to the theory. Okay, so picture this. You've got this circuit board, right? Wires everywhere, resistors, batteries. It just looks like a total mess, a rat's nest. But here's the thing. There's an order hiding in that chaos. There are rules governing how it all works, and we're about to figure them out. And the key, the secret decoder ring for all of this, is a basic rule of physics called Kirchhoff's voltage law. All it really says is that energy doesn't just appear or disappear in a closed loop. Whatever juice the batteries are putting in has to get used up by all the little parts in that loop. It's that simple, and that's our way in. Okay, now this is where things get really cool. We can take that physical law and use it to translate our messy, real-world circuit into the clean, powerful language of math. This is where the magic really starts to happen. So what does that look like? Well, we take Kirchhoff's law and we apply it to every single loop in our circuit. And just like that, boom, we get a system of equations. Each equation is one loop, and those little I variables, those are the currents we're hunting for. We've just turned a jumble of wires into a straight-up algebra problem. But writing out all those equations is kind of clunky. We can clean it up. We can pack all that information into something called an augmented matrix. It's basically just a grid, a neat little table with all the important numbers. The resistances, the voltages, everything we need all in one place. But wait, there's another way to look at this, a more geometric way. The question now becomes, how do we mix and match these column vectors, you can think of them as the ingredients of our circuit, to create our final voltage vector? It's like we're trying to find the right recipe. And that leads us to this, the most beautiful, elegant way to write it all down. A times X equals B. That's it. Our whole tangled circuit boiled down to 3 letters. The matrix A has all the circuit's properties, X is the currents we want to find, and B is the voltage we're putting in. So simple, right? Okay, so here's the bottom line. This whole thing only works, we only get a solution, if our voltage vector B can actually be built from the columns of A. Think of the columns of A as your Lego blocks. If you can't build the B vector with the blocks you have, then there's no solution. It has to exist in the same space that your Lego blocks can build. All right, we've got our elegant equation, AX equals B. So now what? How do we actually find X, the currents we've been looking for all this time? Well, it turns out there are a couple of main ways to go about it. And you kind of have to make a choice here. On one hand, you have direct methods. They're like following a precise recipe. You do the steps and you get the exact answer. Bam, done. But you need to have the whole system in your computer's memory at once. On the other hand, you've got iterative methods. These are more like playing hot and cold. You start with a guess and you just keep refining it, getting a little warmer, a little closer each time. This is awesome for absolutely massive problems where a good enough answer is, well, good enough. Okay, think about what we've done. We found the currents for one specific setup, but what if we change the batteries? What if we want to understand the fundamental nature of the circuit itself? What are the deep, unchanging truths hidden inside that matrix A? This is the moment we level up, from just solving a puzzle to actually understanding the system. This is a huge pivot. We're not just using matrix A anymore to get an answer. We're putting it under a microscope. We're asking the matrix, hey, what are your secrets? What makes you, you? And the secret, it's all about finding these really special vectors. See, most of the time, when you push a vector through a matrix, it gets twisted and turned all over the place. It comes out pointing in a completely new direction. But not these guys, the eigenvectors. They sail right through, pointing in the exact same direction. They might get stretched or squished, but they don't turn. They hold their line. And this little equation right here, AV equals lambda V, this is it. This is one of the most important ideas in all of math. All it's saying is that when our matrix A operates on its special eigenvector V, what you get back is just that same vector V, but scaled by some number. That number, that scaling factor, is lambda, the eigenvalue. It's the stretch factor. Here's a great way to picture it. Imagine you've got a picture of the Mona Lisa, and you do a shear transform on it, like pushing the top of the frame to the right. Almost every pixel gets shifted and is now in a different direction from the center. But think about the pixels right on the horizontal line going through the middle. They just slide sideways, right? They don't change their direction at all. That line, that's an axis of eigenvectors. And since they didn't get stretched, their eigenvalue is just 1. So you see, these aren't just some weird math quirk. Eigenvectors and eigenvalues are like the skeleton of the system. They are the principal axes, the natural directions where all the action is just simple stretching or shrinking. They show you what the system is really doing underneath it all. So why does any of this matter? Okay, let's get to the payoff. Because knowing a system's fundamental essence isn't just a neat trick. Honestly, it's like having a superpower. And I mean, look at this list. Engineers use it to figure out how a bridge will shake in the wind. It's used to make sure buildings don't fall down. It's at the heart of quantum mechanics. It's how facial recognition works. Even the original algorithm that made Google, was built on this. Eigenvalues are, quite literally, everywhere. Let's just pick one to zoom in on. PCA in data science. Imagine you have a crazy data set with millions of different columns or features. It's impossible to make sense of. What PCA does is find the eigenvectors of that data, the principal components. These are the directions through the data that capture the most important information, the most variation. And the eigenvalue for each one tells you exactly how important it is. And this is the mind-blowing part. A data scientist can discover that maybe just a few of these special directions, these eigenvectors, can explain something like 90% of everything that's going on in their massive data set. It's like taking a giant, complicated story and finding the 3 sentences that give you the entire plot. It's a game changer. So that brings us to the big takeaway. We started with a mess of tangled wires, right? But the tool we ended up with, this idea of finding a system's hidden structure, can be used on almost anything. If you can find the eigenstructure of a complex system, you can truly understand it. You can see how it's going to behave. So the final question is, what other complex systems out there, from financial markets to social networks, are just waiting for us to uncover their secrets?